Hello students. In today's class we will learn and review other gates, other gate types in addition to those basic AND or NOT gates that we have studied so far. We are now in part 3 of chapter 2 of our textbook, right? The outline of today's topics are as follows. We will first study other gate types, right? In addition to those simple AND or NOT gates. Also, we'll see exclusive OR operator and so-called universal gates. We'll also see high impedance outputs. Why we may need to consider other types of gates in addition to AND or and NOT gates. We need to study other gates that are more efficient to use than the actual native gates when implementing a circuit, for instance. That could be one of the reasons. And second reason for studying other gate types is that we want to study gates that may require less transistors at low cost and which can operate faster than AND or NOT gates, for instance. Right? Another reason for studying another gate types is that we want to use or come up with a gate that we can essentially use to recreate any logic function and which could provide a convenient conceptual representation of large-scale integrated circuits. Right? Today we'll first study different gate classification, in particular primitive gate and then complex gate. So we classify gates into two classes now, primitive gate and complex. So primitive gate is a gate that can be described using a single primitive operation such as AND or OR plus an optional inversion, right? NOT operation. So these are the primitives. And then complex gate. Complex gate is a gate that requires more than one primitive operation type for its description. Buffer is a gate with the function of f equal to x. And it has the following symbol, x, and then this is the symbol of the buffer, the triangle aligned with f, right? So buffer is nothing but is the same as a connection in terms of Boolean function, f is equal to x. But why do we need to use it? Well, one of the reasons is that the buffer, this connection, can be used as an electronic amplifier, okay, to improve circuit voltage levels and also to increase the speed of circuit operation. Okay, so buffers are used as an amplifier for one of two main reasons: to improve circuit voltage and then the speed of circuit operation. Another type of the gate is called NAND gate. NAND gate. Here, okay, the basic NAND gate has a following symbol, as illustrated here, for 3 inputs. Okay, so NAND can be defined as AND invert operation, right? So first AND, and then apply this symbol. Circle is invert, can be interpreted as invert, right? So look, these are X and Y and Z, and we invert. So again, NAND represents not AND. Okay, the AND function would not apply, as we can see here. So if we apply De Morgan's law to the NAND gate, NAND operation we have seen, we'll obtain invert OR, right? Remember, the De Morgan's law is like break the line and then change the sign, right? So we are breaking the line of inverter and then changing the sign from AND to OR operation. So now we have another view of NAND gate where bubbles are appearing before the, right? This is OR like a symbol, right? So we can call this symbol as OR invert, invert OR, sorry. So first invert and then perform OR. Invert and then OR, perform OR, right? So both AND invert and then invert OR represent the NAND gate. We obtain this form using De Morgan's. Right? And then look, if you have one input to this gate, okay, then NAND gate will generate an inverter. Okay, it can be considered as an inverter. So first, the NAND gates is actually the natural implementation for CMOS technology in terms of chip area and then speed. Right? And also NAND gate is called a universal gate. Okay, a universal gate is a gate which can implement any Boolean function without the need to use any other gates. Right? In picture 24 of our textbook, we can see that we can use NAND gate to implement AND, OR, and the NOT operation. Also note that NAND gates usually they don't have an operation symbol. Why? Because a NAND operation is not associative, and working with a non-associative operation is difficult in mathematics. We said that NAND gate is a universal gate, right? That we can implement all other logic gates using the NAND gate. For instance, this is figure 24 from the textbook. NOT gate can be constructed by one input NAND gate. However, in this case, we can use buffer with invert also. Okay? So single input NAND gate works same as inverter or NOT gate. AND gate can be implemented by connecting a NAND gate to a single input, let's say, inverter, or single input NAND gate. We will see later how we can construct single input NAND gate. The OR gate can be implemented by connecting inputs, okay, to single input NAND gate, or here in this case inverters, to a single, okay, to a NAND gate, two input NAND gate. So we can use NAND gate to implement NOT and OR operators. Here we have another type of the gate called NOR gate. Okay, the NOR gate is also called as OR and invert, has the following symbol, as illustrated here with three inputs X, Y, Z. NOR is short for OR invert, as we can see, OR and then invert, OR of X, Y, Z, and then invert. Okay, NOR represents also not OR. Okay, the OR function would not apply. Okay, again, this circle or the bubble represents the invert operation. So if we apply De Morgan's law, then we get invert and then AND operation, XYZ, invert, and then perform AND. Okay, this NOR symbol is called invert AND, as we know, as we can see, first inputs invert and then AND together. So look, OR invert and then AND invert both represent NOR gate. Right, having both makes visualization of circuit function easier. Like in the NAND gate, a NOR gate with one input degenerates to an inverter. NOR gate also is a universal gate. We can use it to implement any Boolean function. Right? Also, it is as good as NAND gate for implementation in terms of chip area and then speed. In addition, just like NAND gate, we don't have a defined operation here for NOR gate because also it is not associative. Now let's talk about exclusive OR or exclusive NOR function. It's called also in short as XOR. Okay, it's a function that is widely used in logic circuits. It's a Boolean function, right? So exclusive OR function may be implemented directly as an electronic circuit, as a truly gate, or implemented by interconnecting other gate types. And also exclusive NOR function, okay, is a complement of exclusive OR function. And we call these XOR, XNOR as complex gates, while the other gates covered so far are called as primitive gates. So exclusive OR and exclusive NOR gate usually include implementing adders, subtractors, multipliers, counters, incrementers and decrementers, parity generator, and checkers. We will see examples of the use of exclusive OR and NAR, exclusive NAR gates in the coming class, in coming lecture. So the definition of exclusive OR function is as follows. X, here we have plus and then circle, this is a symbol. X and then exclusive OR Y is equal to the following, right? X and Y complement, or X complement and Y, right? And exclusive NOR function is defined as follows, which is equivalent. So here we have complement, and then it is equal to the following, X and Y, or X complement Y complement. So generally, or strictly speaking, exclusive OR or exclusive NOR gates do not exist for more than 2 inputs. Instead, they are replaced by odd and even functions when we have more than 2 inputs. We can see the truth tables for exclusive OR, exclusive NOR function, Boolean functions, right? Here we have X and Y, right? And then the output of the operation. 0, 0, 0, 1, okay, 1, 0, 1, 1. You can see when X and Y is different, the output would be 1. Well, exclusive NOR is the inverse of exclusive OR, right? So 0, 0, 1, 0, 1, okay, 0, 1, 0, 0, and 1, 1 is 1. So exclusive OR is high, or let's say true, when the inputs are equal, same, right? So from this truth table, we can see that exclusive OR function means X or Y, but not both, right? One of them should be true, but not both. Or one of them should be 1, okay, but not both, or 0. So similarly, you can think about the exclusive NOR function as an equivalence function, right? Why? Because it gives 1 or true or also high when 2 inputs are equivalent, 0, 0, 1, 1. In other cases, it's 0. So exclusive OR and exclusive NOR function can be extended to 3 or more variables as follows. Okay, for more than 2 variables, it's called an odd function, or modulo 2 sum, not an exclusive OR function. So in this example, X, okay, XOR Y, XOR Z is equal to the following. And we have some, complement of the odd function is the even function. Okay, this is the odd function when we have 3 or more inputs. So some of the useful identities that define the exclusive OR function is shown here. Okay, X, exclusive OR 0 is X, right? If 2X, 0, okay, X and X exclusive OR Y is equal to the following, right? So these are just, again, useful identities that you may need to know by heart. And simple symbols for exclusive OR, exclusive NOR is as follows. So these are the XOR, XNOR symbol, right? Here we have inverter. Only for 2 inputs in this case. So implementation of exclusive OR using sum of products implementation has the following structure. Here we're using AND gate, right? OR gate, and then inverters. 3 different types of the gate, basic gates. Well, if you want to use NAND gate only implementation, it will have the following structure. Look, we said NAND is a universal gate that you can implement, right, any other type of the gate. So here we are just using 4 NAND gates, right, to implement exclusive OR. In this case, okay, visually we see 5, let's say, gate, 2 inverters, 2 AND gates, and then 1 OR gate. Let me quickly define the odd and even functions as we discussed. So the odd and even functions on K-map form a checkerboard pattern. Okay? In particular, the ones of an odd function correspond to min terms having an index with an odd number of ones. Okay? Ones of odd function have index with an odd number of ones. And then ones of even function here corresponds to min terms having index with an even number of ones. Odd number of ones, even number of ones, right? Index. So these are 2 characteristics defining the odd and even number. Implementation of odd and even functions for greater than 4 variables as a two-level circuit is difficult. Therefore, we use trees made up of 2 input XOR and then OR XNORs, or 3 or 4 input odd or even functions. For example, we can see here, we want to design a 3 input odd function, okay, with 2 XOR gates. So first we factor out this X, okay, XOR Y and then XOR Z, and then the circuit will have the following structure: X, Y, okay, exclusive OR, and then the output of these will go to the next gate. We can use exclusive OR operators as parity generators and checkers. If you remember in chapter 1, we had one example where a parity bit was used or added to n-bit code to produce an n+1 bit code, right? So we could add either odd parity to generate code words with even parity, or add even parity bit, which is okay n plus this bit, right, to generate code words with odd parity. We may have 2 different types of circuit to check code words with even parity or odd parity, right? So odd parity circuit or even parity circuit. Let's take a look at this example. So here we have 3 bit, n is equal to 3, and then we want to generate the parity code words, right, of length 4 with odd parity generator. So for 3 bit x, y, z, we can use the following 2 exclusive OR gates and then generate the parity, right? And then we can have the parity checker circuit defined as follows. So X, Y, Z, and then we have P, right? P. And then the following circuit will generate or check if there is any error or not. Okay, for example, if we have X, Y, Z to be 0, 0, 1, right? 0, 0, 1, then we should have P should generate 1 so that we have even parity, and then error will be 0. If Y changes in this example from 0 to 1 between generator, parity generate, and then checker, then E will be 1, indicating it as error. So this example shows that we can use exclusive OR operator as to build a parity generator and then parity checker circuits. So far, we have considered gates that have only output values, logic 0 and logic 1, 0 or 1, right? Here we will see an interesting structure which is called 3-state buffer, okay, which provides us a third output value, which we refer to as high impedance state, and we denote it as high Z, or just sometimes Z, right? The high Z, high impedance value, behaves as an open circuit, which means that we find that the output appears to be disconnected internally if you look at the circuit. And also, we note that the high impedance, okay, gates with high impedance output have 2 very interesting properties, useful properties. First, the high Z outputs can be connected together, okay, while when we have only 1 and 0, we cannot have them connected together. Okay, provided that we have no 2 or more gates that drive the line at the same time, or opposite, 0 and 1. And second important property of the high Z state, high impedance, let's say state, is that because it acts as an open circuit, we can have input attached to it internally. So we can have this high Z output act as both input and output. This is sometimes referred as a bidirectional input-output. Well, instead of just carrying signal in just one direction, we can have the signal carrying in 2 directions, interconnection between different gates. So having such bidirectional input and output feature can reduce significantly reduce the number of interconnections required in circuits. Earlier, we introduced three-state buffer as one of the primitive gates. The three-state buffer has three-state logic outputs that show different states, exhibit different states. This is a symbol of three-state buffer. So we have input, enable, and then output, right? And then here we have the truth table. Enable, input, output. So as we can see, two of the states are logic 1 and logic 0 of, let's say, conventional logic, right? 0 and 1. And the third state here is a high Z value, which for three-state logic, okay, we refer as high Z state. Okay, 0, 1, and then high Z. Note that this symbol is different, okay, from the symbol that we use for the buffer with this enable connection entering here at the bottom of buffer symbol, right? So also we know that from this truth table, if enable is high or 1, okay, then output is equal to input, which behaves like a normal buffer. But if enable is 0, then output value is equal to high Z, high impedance, regardless of the value of input.